Welcome to the debate. We are at what feels like a major technological inflection point. We're seeing this incredible acceleration in AI capabilities, moving past, the static large language models into something much more complex, multimodal, and I think critically, increasingly embodied.
Absolutely. That shift is palpable. You can see it across all the source material we're looking at today. It's a flurry of activity, from Google DeepMind's latest demos with real-time robotic adaptation all the way to, the staggering jump we see in generative power, like GPT 5.2 creating entire software suites from a single prompt.
And that level of complexity, that versatility, it just raises this profound question for me. Does all this success we're now seeing signal that the industry has finally found the path? The critical efficiency breakthrough needed for artificial general intelligence? I'm going to argue that yes, the current scaling paradigm, combined with this new focus on integration, has proven it's sufficient to rapidly close those remaining gaps. I think AGI is much closer than many people believe.
And I'm going to argue that these are still, at their core, highly sophisticated and specialized engineering feats that are layered over some pretty significant weaknesses. The path to AGI remains long. I think it demands a true paradigm shift, a fundamental data efficiency breakthrough that, frankly, just scaling our current models isn't going to deliver.
Well, let me lay out my case for sufficiency then. The current scaling paradigm, the one fueled by massive compute and data, it's yielding returns that are fundamentally nonlinear. The leap in capability that we're seeing in these generative models, that is the validation of this entire approach. We're not just getting bigger answers, we're getting categorically different answers.
Okay, so give me a concrete example of that. What's a truly qualitative leap you're seeing?
All right, take the test case documented by @Skirano. They tested a leading frontier model, GPT 5.2, and it demonstrated what I can only call genuine generalized reasoning. It generated a complete 3D graphics engine in a single file. That includes all the code for interactive controls, 4K export functionality, the whole thing. That one-shot complexity, the ability to, conceptualize the math, structure the code, and manage the simulation environment all at once, that points directly toward bridging these final gaps. It's building the complex tools itself, not just describing them.
That's an undeniably extraordinary feat of symbol manipulation. It's perfectly tailored for the closed, consistent logic of a digital sandbox. But the real-world integration, that's where true generalized intelligence gets tested. And the evidence there, it suggests we're still just papering over the cracks.
But even the papering is rapidly advancing the effective intelligence of these systems. Look at how intelligence is being distributed. Satya Nadella's demo of the chain of debate application used these multi-model frameworks. DXO is what the source material calls them, to simulate expert critiques. This whole setup was shown to outperform single frontier models by a huge margin in really high-stakes evaluations, specifically healthcare analysis. When you can synthesize and integrate intelligence across specialized models like that, it suggests the necessary comprehensive intelligence is already here. It's just waiting for the right architecture. The scaffolding is the intelligence.
I agree that system integration is a powerful engineering shortcut, but I have to challenge your framing there. Are we truly seeing an evolution in the core intelligence? Or are we just getting better at masking the fundamental inefficiencies and failure modes of the underlying model? My thesis is that these perceived breakthroughs are highly optimized, often stage-managed demonstrations, and that the foundational problems, especially physical world common sense, remain severe. We're building expert tools, not general minds.
So where do you find the strongest evidence for that limitation if the output is so impressive?
You find it in the candid admissions from the teams who are actually working on physical embodiment. Look at that DeepMind robotics demonstration. A robot successfully navigates the problem of manipulating a novel, squishy stress ball. And while the adaptation is compelling, the robotics director, Kanishka Rao, he explicitly acknowledged they still face a, quote, long tail of problems, and, critically, that they require one more major data efficiency breakthrough to get to general-purpose robots. The reason is simple. Physical interaction datasets are scarce. They're incredibly costly to generate compared to the endless sea of text and images we feed language models. Scaling language hasn't solved the physics problem.
But that admission implies that they are close, that they know exactly what the limiting factor is. That sounds to me like a solvable engineering challenge, not some foundational conceptual wall.
But until that breakthrough actually arrives, we have to rely on specialization. Just consider the real-world engineering hacks being deployed today for efficiency. Look at this open-source library called Android Use. This entire project was developed to bypass expensive generalized vision models by performing something called accessibility tree parsing.
And what is accessibility tree parsing in this context?
It's basically using metadata, stuff originally designed for screen readers, to automate complex field operations, like navigating a mobile app inside a truck cab. So instead of relying on a slow, generalized vision model that needs to physically see and understand a button, these specialized tools just exploit the clean, structured data that's already there. And this success story proves that specialized, low-cost solutions are still required for reliable, robust execution in messy, real-world environments. The generalized, vision-heavy AI is just too slow, too fragile, or too inefficient to be practical. The specialist tool beats the generalist model when robustness is key.
Let's dive into that tension, because the capacity to rapidly move between high-level conceptual domains is the core definition of intelligence, and that's precisely what we're seeing in the digital space.
I would agree, provided the domains were truly disparate. But code generation, image analysis, they're deeply rooted in symbolic logic and high-volume structured data. That's the current model's core competence.
But the symbol manipulation has to incorporate real-world physics and abstract concepts to actually work. Consider the application in computer vision detailed by at MeasurePlan. They were able to quickly train a model to count chin-ups, identifying hands, the bar, head position, using simple natural language prompts with tools like RoboFlow and SAM3. That model, the Segment Anything model, allows for this rapid, low-code development. So the model has to understand the abstract concept of a rip, the physics of the human body, and how to track movement robustly, all from a simple text instruction. That's generalization of high-level concepts evolving right before our eyes.
Right, and that's a compelling demonstration. But the digital realm, even with video, is still constrained by the parameters of digital capture. The generalization holds up when the input is predictable. A video feed, an image, a clean block of code. The challenge, as Raul mentioned, is the continuous, non-linear complexity of the actual physical world. That DeepMind demo with the stress ball, it was impressive because it required a vision language action model to generate a sophisticated internal monologue just to handle the plasticity and novelty of that one squishy object. That's computationally intense and requires training data that is fundamentally different from the vast, static text and image dumps that fuel most of these AGI claims.
You keep focusing on these edge cases in robotics, but this sophisticated symbol manipulation applies to all forms of practical engineering and design.
I just don't think it has demonstrated the sheer robustness required by centuries of mechanical engineering. Compare that robotic adaptation, which is still high cost, requires immense training, to something like the Voith-Schneider propeller. This propeller uses spinning blades that continuously change pitch to generate instant thrust in any direction. Its supermaneuverability perfected over 90 years. This device uses continuous, complex mechanical control to handle real-world turbulence, variable loads, things AI still struggles to master with specific, high-fidelity physical training data. We have 90 years of empirical engineering knowledge baked into systems like that. AI has not matched that level of robustness through generalized learning. Not yet. That needs a fundamental breakthrough, not just scaling.
And that tension brings us right to our next point, the efficacy of this multi-model scaffolding. You frame it as a workaround, but I believe this integration is the evolutionary leap.
Well, I see why you'd see it as evolution, but I frame it as a weakness. Frameworks like Nadella's Chain of Debate or the LLM Council, they're fundamentally patches. They're designed to cover for known vulnerabilities, hallucinations, incoherence, in single frontier models. When you need 5 separate models to check each other to generate one reliable healthcare valuation, that suggests the underlying single intelligence is not robustly general. It's highly fallible. It requires a committee of specialists to supervise it. This is sophisticated scaffolding, sure, but it's not an inherent leap in the model's own core capacity.
I would just frame that observation differently. This integration is the evolutionary step. I mean, intelligence, whether it's biological or artificial, is defined by its ability to effectively use tools and aggregate information.
Human intelligence doesn't operate as some monolithic singularity either. We consult experts, we cross-reference, we use specialized cognitive tools. So if we can combine sophisticated core models like Gemini 3 Pro with targeted, commercially relevant applications, the results are transformational.
And where are you seeing this transformation manifest with such decisive commercial impact?
Look at Figma's new AI editing tools. They are integrating their foundation model. They call it Nano Banana in development to provide these seamless functions like complex object isolation and background extension directly inside a web browser. This kind of integration is starting to directly replace traditional highly specialized software like Photoshop. The fact that the market is willing to pivot and adopt these complex integrated AI functions proves the model's readiness to deliver general high-utility capabilities across previously walled-off domains. This market disruption proves operational intelligence.
Utility, yes. AGI, no. And that takes us neatly into our final point: market confidence versus foundational reality. You suggest these massive market movements validate AGI's imminence. I remain deeply skeptical of that correlation.
The market movement, though, is a strong indicator of technical robustness. The rollout of Google's Gemini AI experience directly onto Apple's iPhone and iPad. That puts a best-in-class AI stack into the largest distribution engine on Earth. That level of deployment requires immense, tested confidence in the AI's robustness, its scalability, its ability to handle generalized user requests from billions of people without catastrophic failure rates. Companies just don't enter into distribution deals of that magnitude unless they believe the underlying tech is stable.
And while that's commercially significant, it's primarily a strategic business alignment. It benefits both Apple and Google. As the replies to that news noted, Apple gets a premier AI stack without years of building. Google gets unparalleled reach. It's a strategic hedge, not necessarily a testament to a foundational breakthrough. I think to understand how far we still have to go, we need to look deeper at foundational science.
What foundational science suggests we're still distant?
The kind of unexpected discovery that genuinely shifts the scientific paradigm. So consider the recent study on ultra-clean graphene. Scientists observed that electrons in this material violate the 170-year-old Wiedemann-Franz law, which describes the established link between heat and charge transport.
How does violating a century-old law affect the debate on AI scaling?
Because it demonstrates that the electrons are behaving hydrodynamically, like a low-viscosity liquid, rather than as independent particles. This is a fundamental, new quantum phenomenon being discovered right now. If we are still discovering entirely new rules of physics, allowing tabletop experiments to simulate environments like quark-gluon plasmas, then claiming AGI is close, based solely on scaling our current probabilistic architectures, seems profoundly premature. Our models are built on a bedrock of scientific understanding that is itself still shifting and yielding radical surprises. I don't think we can confidently say we have cracked the blueprint for general intelligence when the foundation is still moving under our feet.
The fact that physics is complex doesn't negate the engineering reality here. We have solved the information processing problem sufficiently to create general intelligent agents that are transformative in the market today. The momentum is just undeniable. Advances in code generation, complex simulation, and especially multimodal integration confirm that current scaling efforts are delivering the generalization needed to overcome that long tail of problems much faster than critics anticipate. The tools are ready, and they're already displacing established software.
And yet, the underlying need for specialized scaffolding, whether that's a chain of debate committee or an efficiency hack like Android use, and the persistent, acknowledged challenge of robust embodied intelligence in the physical world, they both confirm that a true paradigm shift, a genuine data efficiency breakthrough, is still required. We're seeing high-velocity innovation, absolutely, but I believe it's targeted, specialized utility, not fully generalized comprehension.
The source material today, it really underscores this remarkable tension between our two perspectives. We have deep, theoretical innovation, where fundamental rules are being rewritten right alongside this dizzying progress in practical commercial application.
It shows exactly why understanding this landscape requires acknowledging both the dazzling progress in the symbol world and the deep, persistent challenges in the physical and foundational realms. There is clearly much more to explore here, as these two forces continue to collide.